Okay. I guess I'll. Okay. I guess I'll start. So this morning we talked about a particular algorithm, and so what we're going to do this afternoon, later this morning, is talk about a graph algorithm, breadth first search. And so we're going to look at got my notes. How to do breadth first search in parallel and how to do it in a purely functional context, right? So if you remember, the goals that we're trying to get done here are first of all, we want the code to have a sequential semantics. So this I'm going to stepping up for a minute, just to remind you what the overall goals we're trying to achieve in this set of lectures. But still get parallelism. So what we're trying to do is you can reason about the code just like if it was sequential code. You don't have to worry about interleavings. You don't have to worry about the timing of your processes, if one goes slow, whatever. The point is, if the programming language is implemented correctly, it gives you sequential semantics, okay? And we're achieving this by using purely functional programming. Now, you could achieve it in other ways. You could achieve it by using a programming language which has side effects and make sure you have no race conditions, okay? Does everyone know what a race condition is? Okay, so if you have race conditions, it means you've got two things which are accessing the same data, one of which is modifying, and the other which can be either reading or updating it. So you can, and in fact, quite a bit of the programming, I do about half of my programming, or my group does, in C, and half of about ML. But when we write C code, we're very careful to write it in a race-free manner, so that you don't have any interactions. And then you would get the same effect. So if you write race-free C code, you can do it in a fork-join framework. We use a framework called Silk, which is actually built into GCC, G++. And you can just compile it by saying -f Silk plus, and it'll just work. And you've got spawn and join. And the form of parallelism is very similar to what we do here. So you've got basically fork-join parallelism in an imperative language. But if you write it carefully, you can make your imperative code look functional. Okay, so if your code is race-free, it probably looks a lot like functional code, right? Because it means you're not doing a lot of side effects. Because if you do, it's likely they're going to get erased. So sequential semantics. The second thing is we've got a cost model plus provable bound. And this is particularly important if you're doing algorithm analysis. But even if you're just doing sort of implementation of some application, you're probably going to want to know approximately how well it parallelizes, how much efficiency, et cetera. And the cost model is going to get you a long way there. And then within the cost model, we use work and span, and we want basically work efficiency. Right, so that means we do no more work than the best sequential algorithm, or at least as close as possible to the best sequential algorithm, asymptotically. Then we want low depth, low span, I guess we've been calling it. Okay. Typically, I always tell people, at least nowadays, that we only have on the orders of tens or hundreds of processes available to most of us. Unless you were working on a supercomputer or something, you've probably got that sort of parallelism. Probably work efficiency is more important. Because if your work efficiency is off by a factor of 20, and you've got 20 cores, you divide the work by your 20 cores, and you're back to the sequential algorithm. And you've gained nothing, right? Yeah, so this is important. And then given that it's work efficiency, you try to achieve low span. And a lot of the algorithms, like the ones that Umut got to this morning, achieve both work efficiency, linear work, and then logarithmic span. And another goal is as simple as sequential. In fact, a lot of the algorithms that we describe in the course we teach end up being even simpler than the standard sequential version. So for example, the quick sort that I showed you is simpler than the one you'll find in Corman-Lises and Revest. The one in Corman-Lises and Revest has some wacky thing where it like swaps pointers, moving with iteration from the left and the right. Much lower level, right? But they often described at a lower level of abstraction and inherently sequential. There's one advantage of that version, which it can be done in place, but they don't try to abstraction. And this is going to be true when we talk about breadth-first search. We're going to try to abstract away from the way that you might have been taught breadth-first search before. And another thing is sequential as a side effect. So in other words, if we design a good parallel algorithm, like for MCSS, and it's got linear work and logarithmic span, we don't need to design a separate sequential algorithm. It's also a good sequential algorithm. If we design a work-efficient breadth-first search, and it's got good work and span, and if we can keep the constants reasonably low, then we have a good sequential algorithm. Okay, so there's no need, if you have a good parallel algorithm that's work-efficient, to even do a sequential. Especially if we hit all of these goals. If it's work-efficient, if it's as simple as the sequential, if it's got sequential semantics, so it means it's as easy to reason about, it's as easy to code, it's as work efficient, then just run it sequentially. Run your parallel code on one processor. So that's what you can do. So that's sort of the philosophy is really we should just be teaching parallel algorithms and sequential algorithms in special case. So what we're going to look at now is we're going to try to get these things with breadth-first search. So because we want the sequential semantics purely functional setting, okay, we're going to then use our work and span bounds. We're going to try to make it work efficient. We're going to try to make the span reasonably low. As we'll see, we're not going to get this down to logarithmic. In fact, it's a very hard theoretical question, okay, open theoretical question of whether you can get a work efficient breadth-first search algorithm which has polylogarithmic span. So we're certainly not going to solve it here. And we'll see it's reasonably simple, and it's you could use it as a sequential algorithm. Okay, but before we do breadth-first search, I have to introduce one other structure that's going to allow us to get this work efficiency. Okay, because one problem with purely functional languages and purely functional arrays well, can someone tell me what a problem with a functional array is? We've mentioned it a couple times. Mm-hmm.
If you make a change, you have to copy the entire array.
Exactly. So if we make a change, we have to copy an entire array. Right? So the problem is persistence. And the reason we have to copy it all is functional programming is inherently persistent. We have to, when we modify array, we need the old array to stay there. If we reference it, it would be incorrect to see the change on the old version. You have to create a new version and keep the old version around. So we need a persistent data structure, one that doesn't change when someone else makes a change to it. So persistence requires copying. And I'll put in quote because the whole point is I'm going to show why it doesn't. Yeah?
This is probably a dumb question, but why is it that with arrays we can't share the part that hasn't changed like we do with trees?
Why can't you? Well, you'd need a data structure to do that, and that's sort of where I'm heading. Okay, so yes, that's a good point. So in trees, you can share. What you do is you do what's called path copying, because if you make a change on a leaf of the tree, you basically only have to copy the path down to that leaf, and so it only takes you log n time to make an update on a tree. We would still like to get constant time updates. Okay, and indeed, one way to get something that doesn't require a complete copy is to implement arrays or sequences with trees. And as I mentioned, in our library, we have a tree implementation, and indeed, updating that tree implementation only takes logarithmic cost instead of linear, because you don't have to copy the whole thing. You exactly do this copy of a tree, of a path. But we'd like to get constant, so that's the goal here. And so, yeah, so let's look at this. So it requires copying. Can someone tell me in what situation do I not need to copy? When there's exactly one instance. If I happen to know via compiler or some other way that I have exactly the only instance that exists, the only handle is the one that I have, I can update in place. Okay, and there's been a lot of work on this. There's been Paul Hudak back in the basic compiler techniques that recognize when this is true and allow you to do it in place. Many of you might know about linear logic. You can use basically linear logic of various linear type systems in order to enforce single usage. Okay, and that would work. The problem with linear type systems is that then you can't use it in parallel. The whole point of it is it forces you to single thread the sequences. Okay, so there are different ways, and so I'm going to talk about a particular way now, which is a way that we use in our library. And it actually ended up, we published a paper in this in POPL 17, I think. It's with, I think, purely functional arrays, the title of it, with Bob Harper, who of course will be lecturing next week. Bob Harper, me, and an undergraduate student, which is basically does what we do. In fact, I made this comment to someone the other day, is usually the way research and teaching happens is that you do the research, and then after many years, it eventually makes it into your courses, undergraduate courses. First, it makes it into graduate courses, and then it makes it into undergraduate courses. The way it's worked with this course 210 that Umut and I have been teaching it is we've done it in a sophomore level course, and then it eventually makes it into a POPL paper. So, so these ideas actually we did in the class before we made it into a POPL paper. And I have two other papers which are like that, where we took ideas. In fact, one of them we're going to talk about tomorrow. So the solution that we're going to look at is going to work without a new type system. So we don't have to introduce linear types. It's also going to work in the context of parallelism. So you can take your array and pass it to multiple, fork off multiple things, pass it multiple directions, which you couldn't do with linear types, and it'll work correctly. Okay. And what does it mean to work correctly? Well, you won't be able to tell from the value semantics it's any different than pure. Okay, so assuming it's implemented correctly, it'll look like a completely pure array. But under the hood, it's going to use side effects, and those side effects will have different costs depending on the context. So what ends up happening is we're going to have a cost model that's not pure. Okay, so you have a language which is pure and a cost model that's not pure. Can you someone tell me another example of a programming style that has a language that's pure and a cost model that's completely impure? Haskell, laziness, right? In laziness, the cost is not context independent, depending on who forces it first. So I have two expressions, and let's say I can run I could run this one first and that one first. Whoever runs it first will pay for it. So your semantics, if I wrote down a cost semantics for Haskell, okay, you would have to be an impure semantics. You would have to pass around a store and do all sorts of impure stuff just to model what that cost is. Okay, so that's just another example of a pure language with an impure cost semantics. Okay, so the way we're going to do this is we're going to basically keep some form of history of changes. And our goal here is we're going to keep a history and changes, and we're going to distinguish between two. from a pure point of view, an array is an array. But from the cost semantics, we're going to distinguish what we call a version leaf from a version interior node. And so the way that you think about it is you create a sequence at some point. So let's say this is my new. So maybe I have an operation new that creates a new sequence. In our library, the way you create these special efficient sequences is you actually have a function that says from regular sequence. So you take a regular sequence and you convert it into one of these magic sequences which are efficient for updates. So you have a new, and then you might do an update, right? And then you might do another update here. So let's say this was the first thing I did, that's the second, that's the third thing. Then I do another update. I claim that these can all be done in place because I don't have another pointer. I'm basically releasing it. Okay. Well, it's a little careful because what happens if I come back later and then do this update? You know, I would have messed up this one, right? And so if I had done it in place, I would have then seen it here, which would not be a functional semantics. Okay. And then maybe later I come up and do an update here. So that's a sixth thing I do. And then another one here. Okay. The goal is, and this is sometimes called a version tree. Okay. The goal is to make sure that every time that I make an update to a leaf in this tree, it's going to be cheap. So the cheap ones, this one's going to be cheap because when I made the update, this one didn't exist yet. This one was cheap. This one was cheap because they were all made to a leaf. This, remember, the 6 hadn't been added when I did. This is the ordering here. This one is expensive. So maybe I'll put a, okay, this one's expensive. And this one's cheap. Okay. So what we want to do is ensure that each of these updates in the square take constant time. Let's say I'm doing a single update. Or if I'm doing an inject where I'm doing some k updates, I want it to take k time. Time proportional to the number of changes I'm making. And so that's what we'd like to implement. So is it clear what the goal here is? Mm-hmm. And in particular, the cost we're going to want is something like this. We're going to basically create a table. We're going to have various operations. We're going to have sub, let's say that just extracts an element, and update, and what's the last one? Inject. And the cost we're going to aim for is we're going to have work and span. In this case, we're going to have 2 works and spans. I'm going to erase this for a second. This is going to be in the case of a leaf, and this is a case of an interior. And that's with respect to this picture I drew. So if you're making a change, something is a leaf in the tree, in the version tree, it's going to have one cost. If you make a change to a interior node, like when I did this to the 5 or to the 3, it's going to have a different cost. Okay, and so in particular, we all want these to be order 1. And that's going to be the same, order 1, order 1. This is going to be order. Inject takes 2 arguments, so let me write it. Inject takes my thing I'm changing and my set of updates. So this is going to take order the size of just the number of updates. So remember, this is a bunch of integer value pairs here, and we're just going to pay, and it's going to be fully parallel, so it's order 1. And then over here, it's going to be much more expensive. Okay, so in particular, this is going to actually be log n. This is actually be n. Okay, n here, n is the size of my sequence. So let's say these all taking an array. So this is order log n. And this is order size of u plus n. So the number of updates plus the size of my array. This is order log n. So what you can see is, especially for the update, is if you update one of these things, you go back in time and update something that you've already updated, it now becomes as expensive as the old-fashioned just a purely functional array. You have to basically do a complete copy. While if you update the most recent version, it's going to be constant cost. And similar things for the inject. So if inject is on the most recent, it's sort of the same as it would have done in an imperative language. Otherwise, it would be the same as it would be in a functional language, where you have to pay n to copy it and then apply the updates to the copy. Okay, is it clear what that is? Now, you might ask, remember we talked about having a cost semantics. So we could write down a cost semantics for this, and I'm just going to write down one of the rules to give you a sense of how it works. The cost semantics keeps track of which things are leaves and which things are interior nodes. Okay? So it's always very well defined. Otherwise, what I've done is I've done some hand waving about leaves or not. Now, even though it's hand waving, probably intuitively, most of you could very quickly in a piece of code identify which case. You could identify, for example, a recursive iteration that keeps updating the latest version. And you could then also recognize when you go back and update an old version. Okay? So it's not very hard to recognize. But to formalize it, you need a cost semantics that captures this. And like I said, I'm just going to show one rule. And one thing is we're going to need a store. Okay, so the semantics is going to keep a store. And what it's going to be is a mapping from labels. What we're going to do is we're going to attach on each array a label. And in particular, not just each array, but each version of array, we're going to give its own label. And that's how we're going to distinguish the different versions. And we're going to attach to it a label, a mapping from labels to either plus or minus. And a plus is a leaf, and a minus is an interior node. And then, depending on whether it's a leaf or interior node, we're going to pay one of those two costs. Okay. So I don't know how much you did on various forms of semantics, whether you did any with store passing last week. Did you do any with? No? Okay. It's not that hard. So if we look at a so-called big step semantics of the kind I showed in the first lecture, what we say is we have this store, it is our context, and we have some expression. And it's going to map to a new store where we've modified it. And this is how you model in either big step or small step semantics. You're going to probably need a store to model any sort of imperative programming. So if it's not pure, you're probably going to be carrying a store around. If you write down an operational semantics for a lazy language that captures cost, it definitely has to have a store. Because you have to keep track of which things you've actually evaluated before and which ones you haven't. And that has to be stored kept in a store. So it evaluates to a new store and a value, which is what gets returned. And in our case, we also have a work and a span, a work and a depth, a span, on which I think we've been using D for that. Because that's the general form of all the rules. And then what we have to do is just look at every single possible case of this E. And I'm not going to go through them all, but let's just say we have a set. So if this was lambda, and let's say if this was set. And to simplify things, I'm going to assume that the values have already been evaluated. So if this set is going to be on an array. So it could have been an expression originally. But let's say I've already evaluated that to an array. And it's going to be a update, where the update is itself a, an int cross alpha or something. And this is an alpha seek. Right, so we're taking an alpha seek and we're doing this. So the set, let me call it update, sorry. In our paper we call it set, so we're taking this array and we're updating the ith element. Okay, I'm going to erase this now. And what we're going to now have to do is this, let me put a standard bar here that says what are the things we need to know. We're going to assume that that our arrays are actually a pair of things. They're I'll write it down as a little a, which this is a pure array, and a label. That's how we store. So what we do is we keep with each array a label, which is going to identify whether it's, and that label is going to then map to either leaf or interior. And then what we do is we look at this label and we ask, what does it map to? And so we say, if label maps to plus, so we're going to have a separate rule for the case it maps to minus. So if it's a leaf, so this is an A and the label maps to a plus, what we do is we generate a new label. And what this will now map to is a new store. The new store is going to be modified in the following way. It's going to, first of all, this old label used to be a leaf. It's no longer a leaf because I've now created a newer version. I'm now updating it. So the first thing we do is we now make it to a minus. So this is basically saying we're doing this update here. Anyone that still has a pointer to here, it used to be a plus. As soon as I applied this rule, this one becomes a minus. And it's side effecting. So that's why the cost semantics itself is impure. And the new label becomes a plus because it's a leaf. And our value is going to be a pure, let me do this. Maybe I'll do it with update. Hat is the pure version of an update. It takes my little a here, which is a pure array, and updates it with this update here, which is integer value pair. Okay, but actually the type of this I missed something. We also have to pass it around with it. Oh, no, okay. We have to pass it, the label around with it too. Update my little a, u, that's a hat, and it has the new label. So we've created, for example, we've gone from here to here. We've modified this one to be marked as an interior. We created this one, and we've returned both the array plus the indication that it's new, which is this L prime, which maps to plus. And its work is, because this was plus, I go to this particular rule here. So the work is going to be order 1. So let's just write down 1 here, and the span is 1. If this was a minus, then what would happen is I wouldn't have to do this because it's already a minus. Okay, this I would still do, but this cost would be order n instead of order 1. Okay, so that's just a way to show you that in the cost semantics you can formally account for this. And it intuitively catches the notion that if you're modifying something that's it's sort of the first time it's being modified, then it's cheap. If you're modifying something that someone's already modified, then it's expensive. Now the claim is it's easy, well, it's not that hard, to implement something that matches this. And what's even more interesting, and in fact what we spend the bulk of our paper on, is you can do this in a parallel context. That's hard because we're having side effects under the hood. We have to make sure that those side effects are safe. So the algorithms which are needed to do this are themselves concurrent, and we have to then consider the interleavings of instructions, etc. But it's all done under the hood, so the user doesn't see it. But I'll give you just a sense of how this would work at a high level. Let's say I'm simulating an array, Yeah, so this is my first version. And I actually I keep along with this array its current version. So let's say it's version 1, and this is my pointer to the array. So it says I have version 1, and I point at this thing that's also version 1. Then what I do is when I update, if I update the latest version, I make this version 2, and I update this, and this is going to be version 2 here. I update that. This is array. But what I do is I keep a linked list off each element here of all the history. Okay, if any of you have done like databases and heard about logs, you can think of this as a log. It's a history log of what that particular cell looked like at previous times in history. Okay, and it could be a big linked list. And in fact, we store it not as linked lists, but as arrays so that we can do binary search. And that's how we get the log n. But just for the sake of a simple example, we can think of this as a linked list. And what happens is whenever we do an update, we do the update in place. So if I say, now I want to change, I create version 3, it's going to point here. I'm now going to get version 3, and let's say it updates that from a 7 to a 6. So now that's going to have a 6. But what I've stored is a history, and I said, oh, once upon a time, it was a 7. And in particular, at step 2, it was a 7. So each element in that linked list is a timestamp or version number along with what it looked like at that and prior to that version. Okay, and it could be an earlier one here. Maybe at time 1, maybe this 2 also changed that location. Maybe at time 1, it was a 4. Right? And so what I can now do is go, if I'm doing a lookup, if I'm doing a get, a sub, what I can do is I can go, if I'm lucky and I'm pointing at the most recent version, it's constant time, because I just look directly at the cell. And I can tell because I compare my version number to what's in this header. So if I do a look up in this 3, I see that's a matching 3, and I just look it up and I'm done. Constant. If I do a lookup and I don't match, maybe this is a higher number, because over time that number keeps going up. Maybe this is now 20, and I'm looking at some location here. I then have to go back in history and find the appropriate timestamp. If this is an array, you can do that with a binary search, because these timestamps are ordered by time. And that's where the log n comes from, right? So this log n for lookup here, for the work, comes from the fact I do this binary search on the timestamps. If I'm doing it in the most recent, I just look it up directly at the top. If I update, I just update the top. The one tricky part is I can't do this binary search trick with it if I update an old version. If I now update this version and this is at 20, this has been changed a lot in the meantime. So in that case, I actually have to do a complete copy. So if I go and update this, I'm going to just create a complete copy, and it's originally going to, all these are going to be empty. Okay, it's a copy of the contents, not a copy of the lists. Mm-hmm. It could be a linked list, or a tree, or an array.
And we have to access the latest time?
I'm coming in, and my particular timestamp is something. So if I come in and I have a pointer to this one, my timestamp is 2. And if this is 20, then I say I'm not looking at the most recent. So what I'm now looking for is, if let's say I had a sorted sequence, I'm looking for the timestamp that's between the last timestamp before 2, basically, which I can do with a binary search. Or if it was in a tree, I could do it just by a normal tree search. In either case, so I could get this log n bound actually either using an array. And by the way, I need to use a doubling array because I don't know the size of these ahead of time, so I have to do some sort of doubling. Or I can use just like you said, I could use a binary search tree, which would allow me to find the right version in logarithmic time. So I have to find the correct version. Okay.
Can we store it as a hash list
Well, you don't, because you don't know that your timestamp actually appears in there. So you actually have to find the previous one before you. Okay, so if you put in a hash table, maybe the previous one is before me 2 and I'm 7, I don't know I'm looking for 2. I don't know that was the previous timestamp before. So I do need some sort of ordered data structure, either an array or something, either a sorted array or a sorted tree or a linked list, etc. So this is sort of important because what it says is now we can make algorithms in a purely functional setting work as efficiently as in a imperative setting. Because someone might say, oh, there's a general feeling that as soon as you go to a functional setting, you lose a log n factor. Because to simulate an array, you need to do it with a tree. Right? Well, either you lose a linear factor because you copy the whole array, or you simulate it with a tree and you lose a log n. And this is a way to avoid that. So one of the goals in our class is to make sure that the standard algorithms that you would see in a standard algorithms book, Kuhlmann, Lizard, and Revest, or whatever it is, still have the same work. Mm-hmm.
But you're just shunting the time complexity over to the space complexity, right?
This is space efficient.
It is.
It's space efficient. What we did, I'm not going through the detail. What you can do is you guarantee is once there's a total of n list elements here, then you copy. And then you can amortize the cost of that copy against the cost of the creation, so it's amortized. And so the amount of space is never more than twice what it would have been anyway. Yeah.
Do you also need any kind of garbage collection in order to remove some old unused versions?
That's a good question, and it's answered by the same technique. Is what you're saying is, what we say is, instead of doing garbage collection, we can leave the unused versions, but we're going to guarantee that the total number of versions in here is order n, or maybe exactly n, at most n. And so the total number of versions here is never more than this space. So we're never wasting more than a constant factor of space. Okay, even though maybe no one has pointers to any of these versions, maybe no one in the world has them, we're still only losing a factor of 2. And then when it fills up, we copy this over to a new array and we throw everything away. Okay, and we can amortize the cost of that copy against the cost of all the updates we did. Furthermore, this copy is parallel, and so we can do it in constant depth. Okay, it turns out, yeah. You forget the history. Well, you don't. What you're saying is you forget the history. Yeah, okay. If no one has a pointer to this array at all, then you can completely collect this. If there's at least one person that still points to this, then even in the normal semantics, we'd need that space, right? And so it's no worse than the normal semantics. And so, yeah, at the point at which you can collect it is if there's no versions at all that point to this anymore, we can then collect the whole thing. Any questions? Okay, the same, like I said, we can do the same trick with inject. Instead of doing it at one position, we just do it at multiple positions, and it can all be done in parallel. And like I said, the tricky part, which I'm not going to get into, is you can actually take this array and you can fork 2 jobs. In other words, if there's E1 and E2, or in our notation with parallel, this would be E1, E2. Both of these could use the array, both could make an update. And you can imagine that's tricky because now we're doing various side effects on this data structure here, and we have to be careful. But you can make it all work, and you can account for it all in the cost semantics. Okay, so now we've shown you this, and I've shown you we can make update fast. Now let's go into breadth first search. I guess I'll erase this now. Has anyone not seen breadth first search before? Okay, good. So in breadth first search, what we're doing is we have some graph. We're starting at some vertex. And let me just draw some example graph. Okay, and I'm going to I'm going to number the vertices. Let's call this 0, 1. Doesn't matter. 3, 4, 5. So we start at some vertex, and we basically search for everything that's one. First, we start at this vertex. Then we search for everything that's 1 away, and then everything that's 2 away, and then everything that's 3 away. Right? We do it level by level. It's an onion algorithm, right? That's why it's breadth. We're going in breadth. And you can use it, one of the most common applications of breadth first search is for finding unweighted shortest paths. You want to know how many edges there are between any two vertices. You start at one and you do a breadth first search until you get to the other, and however many rounds it took you is the shortest path. It's also used very heavily in various graph data mining things. So possibly the most common thing that Facebook does is a bounded breadth first search. So what they do is they'll go from you and they'll say, tell me all of your friends' friends. That's a 2-level breadth first search. Or tell me all of your friends' friends' friends. That's a 3-level breadth first search, etc. Okay, so probably, what was the data structure you probably used for breadth first search when you learned it in your algorithms course? Well, there was one data structure for representing the graph. Okay, so we'll talk about that in a minute. But what data structure did you use to sort of maintain a queue? Okay. Again, this is an example of where we're going to raise the abstraction. To think of breadth first search as a queue is as ridiculous as thinking a quick sort as 2 fingers on the left and right, which you swap back and forth. It's just the wrong level of abstraction. Okay, because breadth first search makes much more sense at a high level thought as searching in parallel each level, right? It's just naturally. It's when we teach our students this idea, though breadth first search is just inherently a parallel algorithm, we're going to search for everything that's 2 away in parallel. Search for everyone that's 3 away in parallel. Everything that's 4 away in parallel. Now there are some details to make sure that we get right, and that's what we're going to look at now. Because, when we're searching for everyone that's 3 away, these are the things which are 2 away, and they're both going to basically notice that 2 is 3 away, and we want to make sure that we only include 2 once, for example. Okay, so it's not completely trivial, but we'll see it's not very hard. But we should really be thinking of breadth first search as an iterative algorithm where each iteration covers a whole new level in parallel. Okay, the levels are going to be iterations. So I'm going to iterate, 1, 2, 3, completely sequentially. But we can do each level in parallel. And so our goal here is going to be to get an algorithm where the work equals order m equals number of edges. And in general, I'm going to use m for number of edges and n for number of vertices. So we have to go, in fact, well, I guess, maybe even put m plus n. Technically, m has to be at least as big as n, otherwise the graph will be disconnected and we'll never even visit it. But just for completeness. So that's what sequentially. So we're not going to do better than what a sequential algorithm does. We have to look at all those edges. That's sort of optimal. And then the span, because we're going to iterate over the levels, we sort of have to have a factor in here, which is d. D is the diameter of the graph. The number of rounds of breadth first search is going to be proportional at most to the diameter. The diameter of the graph is the longest path in the graph. The longest, shortest path in the graph. So we would like to do basically as many the span should be somehow proportional to the number of levels we search. And this could actually be better if you're doing a bounded breadth first search. Like I said, often Google is just going to say, find everyone that's 3 hops from you. Then this would only be 3, right? Furthermore, in many graphs, this D here is very small. Like in a social network graph, what is it? No one's further from each other than 7. Everyone has like a hop length of 7. Okay, people have looked at like web graphs. The diameter of most web graphs people have studied is around 40, which is not very high. So this diameter is usually low. Now there are graphs which have very high diameter. What's a graph that has a very high diameter? A linked list, right? Okay, that's not a very friendly graph. So this particular algorithm I'm going to describe would not parallelize on a linked list.
Are we iterating through D values? Like we're running it at D equals 1, running it at D equals 2?
Yeah. Mm-hmm. Yeah, so we're going to run it D times. So we're going to take one step. So we're going to run an algorithm that in this particular case, on step 1, we're going to look at 0. On step 2, we're going to look at 1 and 4. And at step 3, we're going to look at 3, 2, and 5. We're going to do this is 1, 2, 3 sequentially, but across here, it's going to be in parallel. So we're going to look at 3, 2, and 5 in parallel. We're going to look at 1 and 4 in parallel. Of course, in this picture, we don't have a lot of parallelism, but if this grows quickly, then you'd get a lot of parallelism at that level. Now, it turns out that there's a little bit of overhead here. So the algorithm we're going to show is actually going to be D times log number of vertices. So that's what we're aiming for. And so if you think about, let's say I did this on the Facebook graph. It turns out the Facebook graph has 100 billion edges or something. So this is something like 100 billion. Its diameter is, let's say it's 10. And so this is 10 times 20. So that's 200. So the parallelism is 100 billion divided by 200. That's plenty. If we've got 20 cores or 40 cores or even 1,000 cores. Okay, so the goal is then to basically be able to do this level by level. And there's a few challenges we have to meet. And where did I write them down? So what we're going to do is repeat over levels. So this is my iteration, and I'm just going to write it informally at the moment. And when I repeat over the levels, I'm going to keep track of 2 things. I'm going to keep track of what do we call the frontier. That's going to be all the people on this last level I just searched. So when I hit this level, the frontier is going to be 3, 2, and 5. Here it was 1 and 4. That's itself a sequence. Okay, and we're going to keep track what the output, by the way, you can ask, well, what's going to be the output of my algorithm? There's various different ways things I might be interested in breadth first search. One is I might number them with their distance. Okay, and I could write a version that numbers them with a distance. I'm going to write a version that actually creates a so-called breadth first search tree. What it's going to do is, I have different colors. It's going to basically have everyone in every vertex point to a parent from the previous layer. So that's going to point to here. That's going to point to here. That's going to point to here. This one points to here. This one, I have to break a tie. I have to choose arbitrarily one to point to. So that's going to point to here. So that's a breadth first search tree. Okay, once I have this tree, then I can do pretty much everything. I can then do a post-processing step where I label them by depth. I can just traverse the tree. So I'm going to call this tree here P. Maybe even write in red. So every iteration, I'm going to update my F and my P. Of course, it's all done purely functionally. And what are the things I have to do? Well, if I have one F from the previous level, the way that I find the next level is I find all neighbors of F. 2, I filter those not already visited. Okay, because when I find the neighbors of f of this guy, let's say 1 and 4 my frontier. Well, 1 is a neighbor of 4, but I've already visited it. Or there could be a back pointer to 0, and so 0, that's I've already visited. I don't want to keep those. Ultimately, the only ones I want to keep are these 3, right? And the third thing I want to do is remove duplicates. And this is a point, is that when I search, when I find the neighbors of 1, I'm going to find 3 and 2. When I find neighbors of 4, I'm going to find 2 and 5. I could just basically flatten those, right? Let's say, in fact, in the code I'm going to write, you're going to do what's sort of obvious. I'm going to keep a sequence of neighbors for 1. So I'm going to have 3 and 2 as my new neighbors, and I have 2 and 5. I just flatten it out. I now have all my neighbors. The only problem is I have this neighbor twice. Okay, and so that's where the remove duplicates is. And that's basically it. So that's what parallel depth first search is going to do. In each iterations, I have the neighbors from the previous round. I use them to find the neighbors of all the possible neighbors. I filter out the ones which have already been visited, and I remove duplicates, and I've now finished that next level. And I repeat that. Now, I haven't gone into any details. In fact, I haven't even talked precisely about how to represent graphs yet. Okay, the way I'm going to represent, what's the standard way in sequential algorithms you represent a graph? What's one way? A matrix. It's not very efficient for sparse graphs, right? So, adjacency list, right? Do you think an adjacency list is a good representation parallel? Well, what's an adjacency list? Typically it's an array of linked lists, right? Do you think that's a good parallel representation? No, right? Certainly not, because let's say you had in the Google graph, Google itself probably has degree 10 million, or much more than that. Probably has a degree 100 million. So this linked list would be 100 million long. If I had to find all the neighbors of the Google web page, and it was a linked list, I'd have to sequentially go down. Linked lists are horrible for parallelism. You used to always write on my slides, no lists. Okay. You're going to do parallelism, forget you ever learned about linked lists. Okay, but it's easy to fix, is instead of having a sequence of linked lists, we can just have a sequence of sequences. You could also have a sequence of trees, and for efficient as a sequence of sequences, but I'll do it with sequences. Okay, the trees would be just as efficient because we're going to be paying that log n extra depth span anyway, so we could afford to traverse a tree of depth log n. But let's do a sequence. So, for example, our graph up there, I've used brackets for sequences. First entry is the neighbors of 0, which are 1 and 4. Let's say it's an undirected graph. Then we have the neighbors of 1, which is 0, 2, and 3. And then we have the neighbors of 2, which are 1, 4, and 5, etc. So conceptually, it's pretty much the same as adjacency lists, except again, when they teach you in algorithms graphs and they tell you it's an adjacency list, and they show you the little linked lists in here and little pointers and tell you it's a tail pointer, wrong level of abstraction. Even if I was going to, in our level of abstraction, even if I was going to use a list here, what I'd call this is a sequence of sequences, and the interior sequence would be the list implementation of a sequence. That's the right input, right? This is a sequence, and it can be implemented as a list, a tree, a sequence, as an array. We're going to implement it as an array here, but that's the right level. So if you ever see linked lists here again, complain. So anyway, if we raise a level of abstraction, this is the same as what you've seen before. Just a sequence of sequences. We're going to use the array implementation of a sequence, so we can access this fast and parallel. A tree implementation would work just as well. A list implementation would not. So now what we can do is, if we look at each of these rounds, let's look at one of these levels and figure out what we have to do. So let's say that my current state, let's say I've just finished visiting 1 and 4, and I'm going to do the next level. So I'm going to have my frontier is going to equal a sequence 1 and 4. So I'm going to keep the frontier as a sequence. Okay? And then I'm also going to have a parent array. Okay, and let's say I initialized it to, probably the cleanest thing to do is initialize it to all nuns. But I'm going to use a hacky thing, and I'm going to put -1s just so I don't have to write the 4 letters and N-O-N-E over and over again. Okay. So initially, it would have been all -1s, but I visited some. In particular, I visited 0. And by the way, typically what you do, I didn't write it there, but for the root, you point it to itself. So 0 points to itself. So 0 is going to point to 0. That's its parent. 1 points to 0. Okay. 2, 3 are -1s because I haven't visited them yet. And 4 points to 0. And 5 is -1, I haven't visited it. Okay, so that's the state of my data structure after, right after I visited 1 and 4. And what I want to do is just show you one step. Now clearly, if I'm going to do multiple steps, I just put this in a recursive routine that goes one level by one level. So let's just look at one step. And I want to convince you what's going to be important is that the cost of this step is going to be proportional to the degree of my frontier. The sum of the degrees of my frontiers. So in this case, 1 has 2 neighbors. Well, actually, it's got 4 neighbors, and 4 has 1, 2, also 4 neighbors. So I should pay sort of 8 units of cost. And if that's the case, the total cost is going to be linear, because I'm only going to visit every vertex once. So I only visit its edges once. So I only visit every edge once. And so the total work is going to be order m, which is our goal up there. Okay, so all I now want to do is show you how I go. In fact, what I want to do is go from this to after the step. My next frontier is going to be, I guess, 2, 3, and 5. Not necessarily in that order, but maybe it's 3, 2, and 5. It might be in that order. And I will have updated, this will be 0. Now everything would have been visited. I guess 2 will point to 1. 3 will point to, well, 2 could either point to 1 or 4. Let's say it points to 1. 3 would point to 1 as well. This will point to 0. And this will point to 4. And then we're done. So this is one step. Yeah? That's right. No, the answer is probably not. That what we're going to do is, within each level we get a lot of parallelism because we can visit all the neighbors of a level in parallel. But we have to go through the levels one by one. And it seems to be theoretically the case that there are I mentioned at the beginning, it's unknown whether there's a work-efficient algorithm, and in fact it seems unlikely that there's a work-efficient algorithm that has polylogarithmic depth, which allows us to visit multiple levels at the same time. Okay. It turns out there are work-inefficient algorithms which have polylog depth. In fact, you can just do Boolean matrix multiply will give you transitive closure, which will give you a variant, basically a variant of matrix multiply will give you an n-cubed work algorithm, which is logarithmic depth. N-cubed is way off of work efficient. We don't want to spend that much time. So that's a good question. That is like, is it possible to parallelize across the levels? And we don't know how to do that. But like I say, most graphs are pretty shallow, so this is perfectly adequate. Any other question? Yeah.
So just again, the nodes get their indexing arbitrarily.
Yes.
Okay. And 2, how does it pick between 1 and 4? Is that also arbitrary?
Yeah. Well, I'm going to show you the way we're going to pick it, but it's deterministic in the sense this is a functional language, so it's going to be deterministic, and the tie is going to turn out to be broken by the inject. If you remember when I mentioned inject, I said the last one wins. So what happens is whoever's last is going to happen to win in this case. But that's a good question, because there is a tie to be broken. The way that we break it is deterministic. It's going to be well defined. Any other questions? Okay, so what do we have to do? Well, it turns out there's not much we have to do, right? There's some base case of the recursion which checks if my frontier is empty. If the frontier is empty, I'm done. Okay. Otherwise, what I'm going to do is I'm going to fetch all my neighbors of the frontier. So let's call that n for neighbors. And what it's going to be is, well, there's going to be a flatten in here. And then there's going to be a map and lambda x dot. What I'm going to do is I'm going to fetch the neighbor of 1. And I've got this representation, so I can just index, let's call this G here. I can index G at location 1, and that's going to give me its neighbors. So this is just G of my let's call this V here. And we're going to map that over our frontier. And then we're going to flatten the whole thing. So what's the output of this is going to be, let me separate this out here. The output of this is going to be, I'm going to fetch 0, 2, 3, and 4, what are the neighbors of 4 are 0, 1, 2, 5 or something. I missed a neighbor of 1. Poor 1, I left it out its best friend. Okay. No one called me on it. Okay, so 0, 2, 3, 4, and the neighbors of 4 are 0, 1, 2, 5. I just grabbed them all and flattened it all. So that can be done in parallel. So in parallel, for everyone on the frontier, I grab all the neighbors. So that's, if you look at, I'm basically just implementing these 3 steps here. Neighbors of F, filter. I'm just giving you one level more detail of how to do that. Remove duplicates. Yeah?
So G changes depending on which D value we're on.
Which D? G is the same. There's a fixed graph. It never changes.
We're fixing, okay.
G is it's just the graph that stays the same. I'm never touching G. And F.
I thought we were looking at slices at a time, though.
That's what the F represents. That's the slice.
Right.
The F is the current frontier. So F stands for frontier. Let me put.
The distinction between current frontier and global frontier is kind of.
I'm not sure what you mean by global. So the frontier changes. So on step 1 it's 0, then it's 1 and 4, then it's 3, 2, 5, etc.
G is kind of fixed regardless.
That's right. G is just the neighbors of every vertex. Good. Yeah. Any other questions? Okay, it turns out that I need to do this little white lie here. Is I actually need to tag each of these vertices with the source of the vertex. And the reason I need to do this is I'm going to need to create this tree, so I need to not only know that I visited 5, but I know I need to know that I visited 5 from 4. Okay, and I could write a little helper function that's tag a sequence with a bunch of values, and it's just going to be map lambda x, and I just create the pair, which is x dot v, so I'm just tagging it with a v and applying it to my sequence S. Okay, so what I'm going to do is I'm just going to wrap this with a tag, and tag I'm going to tag the neighbor of graph of v with v. And it's going to give me something that looks like a bunch of pairs. So it's going to say it's going to give me the destination. So it's going to be, for 1, it's 0, 2, 3, 4, 0, 1, 2, 1, 3, 1, 4, 1. So all I've done is saying my frontier, my next level vertices are 0, 2, 3, and 4, but they were generated from 1. And I would also have the ones generated from 4. So 4 was 0, 1, 2, and 5, right? So 0, it's the other way around. 0, 4, 0, 1, 4, 2, 4, 5, 4. So this is exactly the same sequence that I had before, except I've tagged it with 1s and 4s. Okay, so that's my find the neighbors, and I find the tagged neighbors. Then I can trivially, let me call it neighbor primes, I can trivially filter out the ones which are already visited, right? Because I can basically do a filter, and my function is just going to check if it's visited. So let me do lambda, sorry. Okay, now remember these are pairs, so it's going to take a thing. So it's lambda u comma v dot. And what I want to do is I want to see if this u is already visited. And the way I do that is I have this p, I just look up here, and it's visited if it's a -1. So I only want to keep the ones which are not -1s, right? So I'm basically, this is going to be if p v is greater or equal to 0. Okay, like I said, probably the cleaner way to write this code would be with nones and sums. So this would be as long as it's a none. Oh no, sorry. We only want to keep the ones which aren't visited. So it's if p equals -1. Sorry. This is going to basically return true for everyone that's not visited. And I apply that to my n. And this is now going to be reduced, this sequence, to just the one. So 0 I visited. I'm only going to be keeping 3, 2, and 5. So it'll be 0, 3, 3, 4, 2, 1, 3, 1, 2. Okay, so like we mentioned before, we can visit 3, 2 from 1, and we can visit 2, 5 from 4, and that's what we're keeping. 3 and 2 from 1, 2 and 5 from 4. I should point out everything I'm doing here is linear work in the size of the number of edges that come out of my frontier set. This one's logarithmic span, the flatten and also the filter, and that's where that log n comes in. Okay, so the last thing I have to do is remove duplicates. And I do that with an inject. I do into P prime, I inject into P, n prime. I've now got my new correct P. I've injected basically at location 2 a 1, at location 3 a 1, at location 2 a 4, at location 5 a 4. I'm actually now completely done with my algorithm because I've got this thing set, right? Because at location 3 I inject a 1, which is what I want. At location 5 I inject a 4, which is what I want. The only question is that there's duplicates here, right? I'm injecting this and that. And one of them will win. The way we defined inject is the second one will win. And so I'll end up with, in fact, I guess this is a white lie here because this is supposed to be a 4. The way that I'm breaking ties in this algorithm. It could be, conceptually 2 can either have 1 or 4 as its parent. But the way I'm breaking ties is going to be 4. Yeah?
You're done not when the frontier is empty, but when there are no negative ones left.
Well, is that correct? So the conjecture was I'm done when there's no negative 1s in P, as opposed to when the frontier is empty. It might be unreachable. So you're correct if it's completely connected, but if I know it's connected, I could just do a test for negative 1s. But there could be unreachable nodes, in which case there won't be negative 1. There's actually one step I'm still missing here is, right, if this is not the last round, I have to now actually I have to create the next frontier, which the next frontier, remember, is supposed to be, in this case, I guess I'm going to keep the second 2 here. So it's going to be 3, 2, and 5. I guess that's exactly what I wrote here. And which means I want to get rid of this one. I also want to strip it off of the unnecessarily previous node here. I claim that this is also very easy to do. I'm not going to write it down. It's basically I just read back from P and check if I won. Right? So this guy reads from P and sees in location 2 not 1, but 4. And it says, oh, I didn't win, I'm going to drop out. This one looks in location 3 and it will see 1. It says I succeeded. This will look in location 2, it will see 4, because it's the one that among these 2 that won. And so these 3 will keep themselves in the filter, and the other one will be dropped. So there's one more filter here. And that's it. So these basically correspond into exactly the steps I've done. I find the neighbors, I filter out the ones already visited. I guess I should have added maybe in there, let me make it an exact correspondence. I should have said update P, right? There was nowhere in this high-level description did I say update P. So maybe this should be update P. And last one is remove duplicates. So that's the whole algorithm. Of course, I have to put this in a loop, recursive loop, since we're talking functional languages. And one thing to note, you say I spent this time talking about these special arrays that are efficient to implement. The key place where that matters is here. Other than this, everything else would be perfectly efficient with any kind of sequences. Okay? That inject is important. It takes work proportional to the number of updates and not the size of p. If it took work proportional to the size of p, then the overall work would equal order the diameter, which we wrote down as d, times the n. Because every single inject, I would have to spend linear work, because p is of size n. There's one per vertex. So it's very important that I don't spend work proportional to the whole thing. I do work proportional to the actual number of updates. And that's where it was important to do the optimized version, the version that only takes work proportional to the updates. And furthermore, if you remember, we said it's only if you're updating the most recent version will it be cheap, otherwise it's expensive. This one's always just created p, and then I create the next p, and I never look back at an old one, right? In fact, truthfully, if I had a system with linear logic, linear type system, I could probably implement this in a linear type system. I could force that p to be a linear type. I've only got one handle to it. Of course, I wouldn't be able to do that in ML. I would need a whole new language with linear types. But that would also be another way to enforce this. But it's important that this thing is work proportional to the size of n. Right? Every step in here is logarithmic span. And that's where we get this. So now what we say is we basically do work proportional to the number of edges. We visit every vertex once. So therefore, we visit its edges once. So that's the cost for the vertices. That's the cost for its edges. And that's the total work. And the span is the number of rounds, which is the diameter of the graph. In fact, it could be as small as half the diameter. Because if I happen to start right in the middle of the graph, I'm only going to do half as many rounds. And each one has this log n span for the filter and the flatten. And that's where that comes in. So that's all the overall cost. So we end up with an algorithm that's work efficient. It has maybe not as low as pointed out. Ideally, we'd like this to be polylogarithmic, but theoretically, that seems like a very hard problem. So we've got something that at least works very well on graphs with low diameter, which are certainly a lot of practical graphs have low diameter. It's reasonably simple. Okay. I don't know if you could argue it's simpler than the sequential version, but I think it's at least more intuitive in the sense that the parallel version, like I said, you're thinking of visiting levels at a time. If you had a queue-based version, what you'd do is you'd visit this vertex here, you'd put all of its vertices into a queue, and then you'd visit that one, you put those into queue, and then you'd pop them from a queue at the next level, right? It doesn't give you really an intuition that it's, parallel 1 level, parallel 2 level, parallel 3 level. Yeah, and then we have a nice cost model, although we had to, in order to make this work, we had to extend the cost model with this, these special arrays that have efficient updates on them. But once we did that, and also, remember there's two parts of the cost model. One is the cost model itself, one is the provable implementation bound. Otherwise, I could just make up, I could say, oh, I don't like the fact that it's linear work to do an update in place. Let's just make it constant time, right? So that's the whole idea of the provable implementation, is you don't want someone to say, I'm going to make up some cost, and say, oh, damn, in functional languages, I have to copy this whole array. I'm just going to ignore that and throw in a constant, okay? That's invalid. So you have to prove, and that's what we do in that Popple paper, is we prove that we're able to match those cost bounds. And the way we prove it is we basically show the data structure I talked about, the one with the array and the linked lists of it, and then we showed how all the bounds work in that implementation. Okay, so that's it on graphs, and I guess tomorrow we're going to be starting on trees. So, I'll see.